So gravity is a really important driving force in geomorphology. Lots of things either move under the influence of gravity or they're deformed under the influence of gravity. Lots of geomorphology is about things moving downhill. That's an interesting discussion topic if you want to have a conversation with that about people. How much of geomorphology can you think of that doesn't involve things moving under the influence of gravity? Not all geomorphology, but a lot of it falls under that category. Now, there are some simple mechanisms by which things move, and there are some complex mechanisms, and we can explore them in different situations: glaciers, rivers, mass movements. The same principles apply in lots of different situations. The key relationship that we'll be looking at is the relationship between stress, the applied force, strength, the resistance to that force, and strain, which is a movement that happens in response to the stress, depending on the strength. Gravity plays an important role in that stress, strength, strain relationship in lots of different geomorphic contexts. So lots of geomorphology is about things moving downhill, and that movement is driven by gravity. You could look at a waterfall on the left-hand side of the image here, the lava flow at the top, or the little mass movement at the bottom right-hand side of your screen. All of those are things moving downhill at different rates in different ways, but under the influence of gravity. And when things do move, it's gravity that controls where they stop. Therefore, it's gravity that controls the shape of depositional landforms, whether you're thinking about a volcano, the shape of which is determined by where material of different particle size grades falls out of the atmosphere, or a scree slope, where the bigger boulders roll with greater momentum roll down to the bottom of the slope, and the finer grade material stays at the top of the slope. So you can see that gradual coarsening downwards in a typical scree slope, which is the opposite of what you'd expect and what we saw earlier when we were looking at alluvial fans or water-controlled slopes. But different things do move downhill differently, even though they are responding to those same driving forces. So in this picture, we're looking at a supraglacial stream, water flowing away from the camera across the surface of the edge of the Greenland ice sheet, and we're looking towards the edge of the glacier. So this ice also is moving away from the camera towards the edge of the glacier. But obviously they're moving at different rates in different ways, and in doing so, they're creating different landforms. The supraglacial stream here is effectively carving a valley in the surface of the glacier, and the glacier is working in a very different way to affect the landscape underneath it. But even when we're looking at very different materials working in apparently different ways, the key relationship is the same. It's a relationship between stress, which may or may not be sufficient to drive strain, depending on the strength that it encounters. And complexities in this relationship in different situations, just move myself so you can see what's on the screen there, the complexities arise from the properties of the different materials, and those properties are partly controlled by environmental controls such as temperature. And I put that picture of the lava flow on there because obviously temperature is a major control in determining whether that rock is hot and runny or cold and solidifies. So here's a reminder of some key concepts that we need to think about, and we talked about some of these previously. First of all, we have shear stress, which is a stress parallel to a surface, and normal stress, which is a stress perpendicular to a surface. And we have equations for different circumstances describing the things that control shear stress. And in lots of different situations, as you should find now when you do a little bit of reading, weight and gradient are key controls on shear stress in lots of different situations. So for example, you might be familiar with the flow law for the shear stress equation for ice flow in glaciers, given here tau equals rho gh sine alpha. To simplify that, the driving shear stress is a function of the weight of the ice and the surface gradient. So it's weight and gradient, and the g there is gravity. Likewise, for equations relating the stress, the driving force, to the amount of strain that takes place, Well, we can do a similar thing for those, and typically here, again, we're including a resistance term. So in ice, again, we can use Glen's flow law to explore how ice moves, and E is strain, the amount of movement, and Glen's flow law says that the amount of deformation, or the amount of movement that you're getting, is a function, again, of tau, the shear stress, but here it's the cube of the shear stress, multiplied by this function A, which is a hardness parameter. It depends on temperature. So rather like hot rock and cold rock moving in different ways, warmer ice and cooler ice move in different ways. So we have the motion, the strain, is a function of the stress and a resistance term. That's a nice example. We'll find examples later on, or you'll find examples in your reading where that same kind of relationship applies in lots of different situations. So we have stress, we have a relationship between stress and strain, and we have forces that resist stress, strength, friction, cohesion, etc. And again, those are typically dependent on environmental controls such as temperature. We're going to talk about those in a later session. So gravity is very prominent in, if you like, the physics of geomorphology. That example we just looked at, glacier creep or glacier ice deformation and glacier sliding. The strain, the movement, depends on the stress, the applied force, and the resistance, the strength in the system. The stress, the applied force, depended on the weight and the controlling gradient. But if we think about the strength in the system, that also depends on weight, as well as things such as ice hardness and bed condition. If you're trying to push something, the heavier it is, the harder it is to push. But then if something is trying to make its way downhill, the heavier it is and the more momentum it can gather, the greater the stress is going to be driving it down the hill. So weight is important both as a driving force and as a resisting force, whereas gradient, in that example we just gave above, is a more simple control because gradient controls the stress, drives that stress component. It doesn't play so much of a role in the strength component. So gravity is an interesting one because through weight it's important both as a driving force and as a resisting force, which makes things complicated but interesting when we try to understand how a system is working. Just to carry on that example, thinking about glaciers, if we think about glacier sliding, the driving stress behind glacier sliding, tau is rho gh sine alpha, so it's the weight and the gradient, as we said before, and the resisting force, the friction underneath the glacier, well, that's normally given by rho gh, which is the weight of the ice, the weight of the glacier above any point on the bed, minus the water pressure and multiplied by some kind of friction factor. But I just want to pull out the point here that the driving stress involves a gravity and weight component, but also the resisting force also involves a gravity and weight component. So if you change the weight factor, if you alter the gravity term within these systems, it's affecting both the driving forces and the resisting forces. So the driving force is driven both by weight and by gradient. The resisting force is also controlled partly by weight. And this is something that you can experiment with at home, and I'll try and put up another video later on demonstrating this, but you can try this out for yourself, sliding objects down sloping surfaces and changing the weight. So use an empty cardboard box and put different amounts of weight inside it and see how changing the weight modifies its propensity to slide downhill under any given gradient. So I've been talking just about glaciers so far as a convenient illustration for these points, but you can take the same ideas and apply them in lots of other situations. It isn't only glaciers that behave this way. So for example, we'll be talking about mass movements later on, and mass movements, landslides, avalanches, soil creep, they again respond to exactly those same controlling factors, the driving stress, the resisting strength, and the relationship between the two. And that's something that you can do a little bit of independent reading about to compare these different systems and how they work, but how they all have the same key factors involved. I always find it interesting to look at pictures like this where we have a glacier on the left-hand side. This is the summit of the volcano Cotopaxi in Ecuador, and here on the right-hand side we have a little mass movement on a hill slope in southern Spain. Here's a diagram below illustrating what the key components are of that morphology of that feature. But that diagram, The morphology of this feature could also apply pretty well to this glacier on the left hand side there. So as it says on the slide, if I just move myself again, we're looking at different materials at very different scales, but in a way we're looking at connected or similar processes and similar morphologies, and part of the reason for that is because we're looking at similar controlling factors between those two systems, so those two situations. So just to clarify that, we've seen previously for glaciers now that tau equals rho gh sine alpha, the driving force is a function of the weight and the gradient. The friction also includes a function of the weight. So stress, weight, friction and gradient are key controls on motion. The question now, well, I've put it to you, that the same controls apply in different situations, such as hill slope processes. How does that work? Well, if you go and look up landslides, mass movements, hill slope processes in the textbook, you won't find the identical equations as I've given you for glaciers. But when you see the equations that hill slope geomorphologists typically use, you'll find that even though the terminology is a little bit different or the symbols are different, the basic layout is the same. So in hill slope processes, you'll typically see equations that look like this for the driving shear stress on a hill slope. T equals, or tau equals W over A sine alpha. What's that mean? Oh, it's different from that, so that looks different surely. No, because W over A simply means the weight over a given area. So that's pretty much the equivalent of the glacier people talking about rho gh. It's really just the weight of the bit of hillside that you're interested in. And then sine alpha, well, that's a function of the gradient again, just like the sine alpha for glaciers. So the shear stress affecting a glacier is the weight of the material, and the gradient, the shear stress affecting mass movement, is the weight of the material over a given area and the sign of the gradient. Likewise, in hill slope processes, the strength factor, won't go through the whole equation in any detail, but I just want to pull out again that weight is an important component in the strength of the system as well as in the driving shear stress affecting the system. So in hill slope processes, mass movements and landslides, once again, weight increases both the stress and the strength. So it's another complicated factor where if you rain more onto a hillside or you put a building on a hillside, that will be increasing the driving stress, but also potentially it will be increasing the strength. So as an applied problem in geomorphology, this is quite a complicated area to think about and to look at. So at the risk of being repetitive, but just to pull out the key points here, the driving force is in lots of different situations. The stress is controlled by gravity, weight, gradient. The resisting forces, the strength, controlled by, again, weight and the properties of the materials and the properties of the boundaries between different materials, friction, lubrication, for example, at boundaries between one material and another. So the key point here is that the same basic relationships and equations, if you want to go down the equations route, but the same basic relationships apply for mass movements as for glaciers, and you can apply them to other things as well. And the key point for this whole session is that if you can understand a few basic rules about how geomorphology works, you can understand all of geomorphology. You don't necessarily need to learn a whole different set of stuff for glaciers from what you've learned for rivers or from what you've learned for mass movements and landslides and so on. So we'll carry on exploring those basic rules now as we begin to look at a few more specific case studies in the following sessions.